Okay, so we're going to wrap up chapter one today, or at least get very close to it. This is section 1C. What we're going to do here is review trigonometry. Now, we don't have to get too terribly in depth here. We just want to make sure we understand the basic concepts. So while this section here, if you look through it, is fairly technical, what I really would like to do is just focus on the highlights so that you still have a refreshed memory of how these functions work, because we will see them again in the future. So here's the list of the standard trig functions, and it's probably bringing back some memories. Maybe they're good and maybe they're not so good. So what you want to do is try to remember how they're defined. So let me draw a little diagram here. And you may have seen this before in your travels. All right, so here's a right triangle. It's called a right triangle because this angle is 90 degrees. And let's just say this is 30 and this is 60. Don't forget, a triangle has 180 degrees. These all have to add up to 180. So imagine that we're interested in calculating the trig functions for 30 degrees. So think of it as the sides in the following way. Relative to 30 degrees, this would be the opposite. This would be the adjacent side. Adjacent means it's right next to it. And then this is what we call the hypotenuse. Oh, yes, the hypotenuse. All right, so I'll just write these in as well. O is the opposite side, or just the opposite. And A is the adjacent side, or the one right next to it. So all of the trig functions can actually be defined in terms of these three sides. And actually, you only have to memorize two of them, because the others are really functions of the first two. But I mean, it's good that you remember them all. But so first of all, the sine of any angle theta is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. Okay, the tangent is the opposite over the adjacent, which means, if you look at these closely, this can be thought of as simply the sine over the cosine. You can see, because if the sine is defined as O over H, the cosine is A over H. These H's cancel out and you're left with O over A. Now the next three are essentially inverses of the first three. In other words, there's six altogether. So we just put these back. Sine theta is O over H. Cosine is A over H. And then finally, tangent is over A. Now you recall that there are three more trig functions which are listed up here: cotangent, secant, and cosecant. So it turns out the cosecant, which is abbreviated CSC, is simply the inverse of the sine. The secant is the inverse of the cosine. And finally, the cotangent, as you could probably guess, is the inverse of the tangent. So since the tangent is a function of the sine and the cosine, and all three of these on the right are functions of the ones on the left, this is what I mean when I say that you really only have to memorize the first two. The rest of these are simply functions of these two trig functions. But altogether, there are six. Now, by the way, if you look at your calculator, you'll notice it does not have any buttons for cosecant, secant, or cotangent. And that's the reason why, because you can just calculate the inverses of the sine, cosine, and tangent. And the manufacturers of the calculator, they know that they have very little space. They have nothing, no room to waste. So they're not going to put anything in here unless it's absolutely necessary. But they do have the sine, cosine, and tangent. Now, we're going to get to this in a bit, but I just want to remind you that when you calculate these trig functions, it can be done with respect to a measure called radians, as well as angles or degrees. So because it could go either way, your calculator has two modes. It has a degrees mode. Let me just go look at it on the TI-84. If you go to the top under mode, which by the way, it's backwards, but you can still see that it says the word mode there. That's kind of awkward. Yes, it's backwards. If you go down there to the very top, the third, oh my God, you can't even see that. Yeah, oh no, because my finger erased it, that's why. All right, there we go. So the third from the top, see you've got the option of doing either radians or degrees. Okay, so you can choose which one you want. Now just remember, and we'll discuss this in a few minutes, radians are all functions of pi. They're all pi or some function of pi. They're a different measure than degrees. For some applications, degrees are more convenient. For some applications, radians are more convenient. That's why we use them both. So just be aware, though, that you can tell your calculator which one you mean before you do any calculations. If you don't tell it, you're going to have a problem, okay? So now, by the way, even the iPhone has this. If you've never looked at this thing, it's actually quite powerful. I think I mentioned this the other day, that yes, there's a calculator on there. Oh my God, there it is. And when you hit the button, you'll say, wow, that's not very impressive, but here's what you have to do. You turn it on its side, and suddenly you have a full-blown scientific calculator at your fingertips. If you look in the extreme bottom left-hand corner, let's see if I can get that up there. No, it's a little, yeah, the camera isn't that great. It's okay, but it's not for this kind of precision work. Well, take my word for it. In the bottom left-hand corner, there's a button that can toggle back and forth between radians and degrees. And then once you set that properly, you can calculate all the trig functions you want, even on the iPhone. Okay. So that iPhone, I'm telling you, there's going to come a time when you don't need anything else but the iPhone. It can do so many things for us. But anyway, we're going to start by just, oh, by the way, I almost forgot about this. There's a mnemonic device which you may have been taught at some level that helps us remember these trig functions. I'm just throwing a new slide here. It's kind of silly, but of course, a lot of mnemonic devices are silly. So the way the story goes is that, depending on who you heard it from, the way it was told to me, whatever grade it was that somewhere in the mountains, the Andes Mountains, it was for some reason, travelers discovered this enormous statue that was left behind by an ancient civilization of a right triangle. And this triangle has the name Sakatoa. Now you might say, well, what is that all about? Well, here's what it means. The sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. Again, it's just pure silliness, but it works. I'm telling you, I mean, it's been decades since I learned this, and I haven't forgotten it. Once it sticks in your memory, it's not going anywhere. So if you've never heard of this before, this is a good way of memorizing the trig definitions. I mean, you maybe memorize it the normal way, but that isn't going to stick as long, I don't think, as a mnemonic device like this one. Anyway, so we're going to formally define what we mean by the word angle. So what we're going to do is just imagine you've got a ray. And remember, we have lines which go on forever. A ray has a specific starting point, and then it goes on forever in whatever direction it faces. Okay, so this is a ray. This is a line. It goes on forever in both directions. So if we have two rays coming together at a common point, this theta is the angle between them where they meet. And so everything in this diagram has names, by the way. We're assuming that we know which direction we're going, by the way. In other words, if here's the first ray, we'll call it ray 1, and we're moving towards ray 2. So we have an initial side, a terminal side, and the point where they meet is called a vertex. And the angle represents how far we have to go to move from one ray to the next. Now, because a circle is defined as 360 degrees, the angle here is the proportion of a full circle that this represents. In other words, if we went let's say 1/10 of the full circle, that means this is 36 degrees. So that's really all that it means. It means how far did we travel relative to a full circle to get from one side to the other. If we would go around an entire circle, we went 360 degrees. If we go halfway around, that would be 180. And so that's where these numbers are coming from. Now, here's something. Oh, and here we go. Here it's being drawn with respect to the axes. So typically, we try to have as our vertex the origin. It just makes things so much simpler. It doesn't have to, but in principle, almost every angle you'll ever see is based on that origin. So here, it looks like this. Now, to get through the first quadrant, and don't forget, these are the 4 quadrants. Each one is 90 degrees. Looks like we went halfway into the second quadrant here. So that means that this angle is 135. Okay, all the way through the first quadrant, halfway into the second quadrant, 135 degrees. And then, of course, in the next diagram, we're going to see 90 degrees just means literally moving to the vertical axis. Oops. Right, exactly 90 degrees. Now, here's where it gets interesting. If you notice, we go in this direction. Let's say we went all the way into the horizontal axis. This would be 180 degrees. It's understood with this measure that we're moving in a counterclockwise direction. But what if that's not the case? What if instead something like this had happened? Ooh, we're going clockwise. What do we call this angle? Well, it turns out that the rule of the way this works is that if we are moving in a counterclockwise direction, the angle is positive. If we are moving in a clockwise direction, the angle is negative. Negative angles, interesting. So that's how we can tell them apart. Okay, so like here's an example of this. Suppose, or for the angle negative 135 degrees, that means that what we've done is we've gone in a clockwise direction. Sorry, 90 degrees to get to the fourth quadrant. And then halfway into the third quadrant is 45 more degrees. So these add up to 135, but because we're going in the clockwise direction, this angle is defined as negative 135 degrees. You know, it seems strange that there can be negative angles, but because there's a concept of direction here, we can go in either direction. Now, by the way, I just as a quick fun aside here, I just want to remind you that this direction is defined as clockwise. And of course, the other direction is counterclockwise. Here's the big question. Why? Why isn't it the other way around? Okay, in other words, why was this direction chosen as clockwise and the other to be counterclockwise? Well, it turns out there's a very good reason for that. And so I'm going to show you why these names came about. But in order to do this, I need a special diagram from Google. Now, I'm sure you've seen these before. A sundial. What is a sundial? Well, this is how time was told for centuries before clocks were invented. So you might say, well, so what? What does that have to do with anything? Well, here's the important detail. In the northern hemisphere, as the day progresses, the shadow cast by the sun is moving in this direction. As the shadow moves to the right, this direction, it's getting later in the day. So what that means is that when clocks were first introduced, they had to figure out what to do about the hands, and they decided to make the hands go in this direction because it follows along what they were used to from sundials. In other words, this made sense to everybody that the clock hands would go in this direction because this is how it always was with sundials. So that's how that came to be known as clockwise. The interesting, fun part about this, though, is that in the southern hemisphere, below the equator, it's the other way around. The shadow of the sun goes the other way. And also, so does water draining down a sink. If you pour water into a sink in the northern hemisphere, it follows a clockwise spiral down the drain. In the south, it goes the other way around. So in other words, if sundials had been invented in the southern hemisphere, then the names clockwise and counterclockwise would refer to the opposite of what they do now. So it's because this was invented in the north that we have the words clockwise and counterclockwise. I thought you'd find that interesting. So anyway, But with respect to angles, you might have thought, well, you know what, positive angles then should be clockwise, right? No, it doesn't seem to have worked out that way. I'm not quite sure what happened there, but the way things are defined in geometry, counterclockwise means a positive angle, clockwise means a negative angle. Okay. So here we have the standard angles when we go into another quadrant. Oh, by the way, if the line stays where it is, if it doesn't move at all, we can think of it as either 0 degrees or equivalently 360 degrees, because if you went around the entire circle, you'd end up right at that exact same spot. Going through the first quadrant brings you 90 degrees. The second one is 180. The third one is 270. These angles, I'd never heard of this term before. I looked it up in Google. Quadrantal angles. You don't have to worry about that, but I just thought you might want to know. Okay, now here, radians, degrees. The most important thing to remember with this is that pi, in my opinion, the best way to mentally think about radians is that pi radians is the same thing as 180 degrees. All the rest just follow along algebraically. So if you wanted to know, for example, 72 degrees equals how many radians, it would be 72 over 180 pi, which is oh, we can still reduce it even further. Two-fifths. Okay, after all that work, it's 2/5. Okay, so in other words, no matter what angle you have in degrees, you can easily convert it into radians by essentially converting it by dividing by 180. So in this case, if you went to your calculator and type 72 divided by 180, it's 0.4 or 2/5. Okay, so that implies actually we can divide out both sides by pi. If you, oh, and don't, by the way, don't forget that the pi is equal to approximately 3.141. So in other words, what I was trying to get at here is that 1 radian so if you take 180 and divide by 3.141, etc., it's approximately 57 degrees. A radian is approximately 57 degrees. If you're wondering, you know, like it's roughly, it's slightly more than 57 degrees. I don't know, I'm not sure exactly how this came about. We could probably find out. I'm sure there's a video about this on YouTube, but I think most people agree that degrees makes the most sense because that's what we're used to. It's almost like trying to go back and forth between Celsius and Fahrenheit. You know, when you go to a foreign country and you hear the temperature in Celsius, you have to sit there and mentally calculate or get your calculator out what the temperature is in Fahrenheit. Because that's what it has an actual meaning to you. I can visualize what 72 degrees means. I can't visualize what 16 degrees Celsius means. It tells me nothing. So I have to convert it. All right. Well, anyway, enough of that. Now, By the way, let's take a look at this diagram for a second. I think you'll agree. Now remember, angles are defined as traveling from one rate to another. In both of these cases, we have the initial side. Here, this is called the terminal side. The two angles have a common terminal side, which implies that they are, in fact, the same angle. But this one, because we're going in a counterclockwise direction, is considered to be positive 140. If we go this side, we're going 90 degrees to the first quadrant, 90 more degrees to the, sorry, not the fourth, 90 more degrees to the third quadrant, and then another 40 into the second quadrant. So they add up to 90 plus 90 plus 40. It's 220, but because we're going clockwise, we call this negative 220. So what this implies is that they're both the same angle. So they both mean the same thing. It would be, like saying going north a mile and then east a mile is the same as going east a mile and then north a mile. You're still going to get the same point. So these are, since they have the same terminal side, we call these coterminal angles. Because they both have the same terminal side. So let's just look at one more. Now let's try $170 in this direction. And this would have to be 10. That's going to be negative 190. So 170 and negative 190 are coterminal. Now, so that you don't have to draw the graph every single time, here's something that I want to point out to you. For any two coterminal angles, the absolute value of the angles add up to 360. So let's go back and double check that. For like here, for example, if you notice 140 and negative 220 are coterminal, if you forget about that negative sign, 140 plus 220 is 360. And you'll see the same thing is true here for 170 and negative 190. Without the negative sign, they do in fact add up to 360, so they must be coterminal. Because they're coming at the same point from two different directions, and both of them then represent basically two parts of a circle. Okay, so you got that out of the way. Now, reference angles. Oh, you know what that reminds me? We need to remind ourselves about some adjectives that describe angles. If you notice here, they're calling this an acute angle. So let's see if we can make up a little chart here. Just in case you've started to figure out. So acute is less than 90 degrees. Okay, now I have to confess I've started to forget some of the others, so we're going to look it up on Google. Here it is. All right, great. Acute is less than 90. Oh, 90 exactly is right, of course. Obtuse is more than 90, less than 180. Now there's actually, there's officially, there's a symbol. I don't know if I have access to that for degrees, I mean. Oh, here it is. I like that. I'm going, whoop. It's strange how it takes up so much space though. Yeah, I don't know what that is, but anyway, it'll be just quicker and easier. I think I'll just do it like this. The right angle, of course, is 90. Obtuse is more than 90, less than 180. Okay, and then straight. Oh, okay, all right. I've never heard it called out, but all right. I mean, it makes sense because it means you're going exactly through two quadrants. Now we need the rest of them. Oh, I think there's more. Reflex. Wow, I never heard of that one before. And then less than 360. Just in case these show up. I mean, like I said already, we saw the word acute, and we will need to remember some of these. Of course, right angle, nobody's forgotten that one. All right, that'll do. So anyway, now here's the thing about angles. Because they refer to how far we've traveled around the axes, there can be different angles that refer to the same distance. So what do I mean by that? Let's say, for example, this is 30 degrees. Okay, we go from the origin, the horizontal axis, up to this angle of this line segment, ray, and we've gone 30 degrees, 1/12 of the entire distance around a circle. But what if we did this? All the way around the circle and then back to the same spot. That would be 30 plus 360 is 390. So that it is telling us that 30 and 390 are the same angle. Ooh, that's tricky. So there's different ways in which the same angle can have two different measures. So we're going to introduce this concept called a reference angle. So what we're really aiming for is the smallest acute angle that can be formed from the terminal side and the horizontal axis. Now, what does that mean? All right, let me show you this chart and it'll start to make sense. So within the four quadrants, these are the formulas for calculating the reference angle. So let's say I don't have any examples here. Well, we better make some up. All right, so we'll look at a few examples. So the reference angle of 60 degrees, according to this diagram, the reference angle in the first quadrant is the angle. So you don't change anything. Okay. But when we get into the later quadrants, for example, how about 105 degrees? All right. So this is telling us here we're going to take 180 minus that angle. And so the second quadrant, the key to the whole thing here is that the second quadrant, 105 is in the second. So let's take a look at it and see if we can reason it out. What they're saying here is that the reference angle is 75 degrees. Now they're not, by the way, they're not saying that 105 equals 75. We have to be careful of that. It's not like this one, where these 2 degrees are actually equal to each other. This is different. What we're basically saying is that the smallest angle that can be formed from the terminal side and the horizontal axis. In other words, what they're telling us is this. That's where it's coming from. How far would we have to go to reach that horizontal axis from where we are? Okay, now the third quadrant. The rule is angle minus 180. Okay. So let's try one of those. Altogether, this adds up to 210. The reference angle, according to this chart, is the actual angle minus 180. And that means 210 minus 180, 30. Now, that's because, remember, we're trying to figure out how far it takes to get back to the horizontal axis. That means this direction. So it's the distance to get back to the horizontal axis that we're aiming for. And then let's do an example in the fourth quadrant. It could have been drawn better. Okay, so that's a 300-degree angle. Now, what do we have to do to get back to the horizontal axis? And the rule, according to the table, is reference a 360 minus angle. In the fourth quadrant, 360 minus the actual angle. $60 as we predicted. So every one of the quadrants, we know what to do with every one of the quadrants. Now, of course, for 0 and 180, if we're already on the axis, then the reference angle would just be 0. Now, we have the same rules for the radians too, but all you're really doing here is converting radians into angles or angles into radians. So I'll tell you what, let's do this. I'm going to draw another picture. And I'm going to bring together the rules for finding a reference angle, that is. For both cases, okay. So for this one, it's the angle. Now that's going to be the same in both cases. For the second quadrant, it's 180 minus angle. And then that means here it would simply be pi minus angle. In the third quadrant, it's angle minus 180. Which implies in radians, it's angle minus pi. Oops. And then in the last case, the last quadrant, it's 360 minus angle. Or 2 pi minus angle. All right. So now the next group, the next block is actually a series of diagrams that are designed to help us um, prove different angles. For example, the sine of 30 degrees, the cosine of 60 degrees. I don't think we can justify spending the time on this part. We just need to remember how these trig functions work. Okay, so I'm going to skip ahead here a little bit. Now, I do want to point out that if you need to know, for example, the sine of 90 or the whatever, you can just look them up on your calculator. So I do want to review a couple more things. The Pythagorean theorem, which I don't think anybody in the history of the planet has ever forgotten. Um, let's jump ahead a little bit here. So yeah, you can read through this part if you want, but it's basically trying to explain to you how and why these sines and cosines have the values that they do in terms of geometry. So oh, by the way, there's this wonderful table here. Suppose that you didn't, let's say your calculator batteries died. What this chart is trying to show you is that for any angle, whether it's degrees or radians, this ordered pair, it turns out that the x coordinate is actually the cosine of that angle, and this y coordinate is the sine. In other words, what this is telling me is that the cosine of 60 degrees is a half, and the sine of 60 degrees is radical 3 over 2. So you can use a chart like this to look out what you need. The only issue with the calculator is that if you went into there and said, show me sine 60, it's going to find the right answer, but it's not going to call it radical 3 over 2. It's going to give you the decimal equivalent, which is 0.8660. So that's the only awkward part, I would say, about using the calculator for these trig functions. But you can figure it out if you needed to, but charts like this are very helpful for certain types of situations, but you can always lean on your calculator. And I'm sure Symbolab will do the same thing. In fact, let's ask Symbolab for the cosine of the sine of 60. I don't know how it's going to react. I guess if you just say 60, it'll assume you mean degrees. Oh, you know what? I think I was supposed to say y equals. Oh, see, now that's good. I mean, it does say radical 3 over 2. So that way, and if you need the decimal equivalent, you can do it yourself. So this is good to know. And just out of curiosity, what I'm going to do now is ask it for not sine of 60, but pi over 3. I want to see how it reacts to that. I have to assume that once we toss in that pi there, it will figure out that we're referring to radians, although there doesn't seem to be any button here that lets us tell it which one we mean. All right, let's try pi over 3. Pi over 3. Yeah, it works. How do you like them? All right, well, that's good to know. um, all right, what else should we cover? Oh, the domain and the range. In case you're wondering, I'll tell you. Let's take a quick look at a graph of before we even get into that. Sine x and cosine x. It's just a bunch of repeating waves, I guess you could call them. And if you notice, the entire real number line is covered. In other words, there's no restrictions on X. As far as Y is concerned, you'll notice that it can reach, Y can reach +1 or -1 or anything in between, but that's it. So the range is the closed interval between negative and +1. The domain is all the real numbers. If you tried the graph of the sine, a cosine rather. Oh, one more thing. Let's pay close attention. It cuts to the 0 right here. Right, it cuts to the origin. How about this one? Oh, wait, sorry. I keep forgetting. You can't just type it. You have to say go. There you go. This is what I wanted you to notice. On the vertical axis, before it was 0, now it's 1. So essentially, they're the same shape, except they're off. It's like they're out of phase with each other. So it's very similar, but it starts and ends at 2 different points. Okay, so that means the domain and range will be the same for both of them. Now here, I've already mentioned this earlier, how to calculate the tangent, cotangent, secant, and cosecant in terms of sine and cosine. Okay, so tangent is sine over cosine. The cotangent is the inverse of the tangent, but that in turn means that it's also equal to the cosine over the sine. Now, why would that come in handy? If you've got a very complex equation with a lot of trig functions in it, this might help us simplify it. If we rewrite it this way, for example, maybe one of those terms can cancel out or something like that. So it's good to be aware of these identities. The secant is the inverse of the cosine. The cosecant is the inverse of the sine. All right. Trig identities. And yeah, like this is what I was referring to. If you had something like this, the secant over the tangent, if you rewrote these in terms of the other trig functions, you can see here the cosines cancel out. You're left with 1 over the sine, and that in turn means the cosecant. Okay. Now, the Pythagorean theorem, as you all know very well, is very simply everybody remembers. Pythagorean is that a squared plus b squared equals c squared. It turns out that this implies at least 3 different relationships between the trig functions that, again, could come in handy. The one that you're probably most likely to be familiar with is this one. The cosine squared of any angle plus the cosine squared of any angle adds up to 1. Okay. And then if we do some algebra on this, we also get the following 2 versions of this. 1 plus the tangent squared equals the secant squared. Okay, and we algebraically did this by dividing both sides by cosine t squared. And finally, we also have cotangent squared plus 1 equals cosecant squared. And that's because we can divide both sides of the original identity by sine squared. Okay, and that's why this is true. You're not, now we're not going to spend, like I said, a whole lot of time with trig functions, but sometimes it can be helpful to have these, especially, well, we'll see what's coming, but these can be helpful. All right. So I think that that's probably all we need to say about trig functions. Look at some of these at the end. Oh my God. But so that will be it. Now we're done with chapter 1. So finally we're ready for limits in chapter 2. So chapter 2 will not be nearly as long as chapter 1. One was really trying to squeeze in a lot of background that we need plus review. It'll be the chapters will be quicker after this, okay? Because we only have 8 weeks, and so, but yes, we needed to go through all this to refresh our memories and to learn some new ideas. But now going forward, the chapters will be shorter. So don't forget, the first problem set has been posted, and you should have it ready by Tuesday night. And we'll try to focus or have just one assignment for each chapter, or sometimes 2 chapters, depending how long they are. So I guess we'll leave it here. Now, like I said, next time we meet, we'll be looking at limits. And limits, we're not going to use them as such. We're not going to solve problems with them. What we're using them for is to help us understand more complex concepts. A lot of what comes after that is based on the notion of a limit. So it's important to understand their properties, but in practical applications, you're not likely to end up taking limits. They're really, like I said, meant for deriving results. But understand that a lot of what we're doing could be expressed in terms of limits. So it's an important tool, but what comes after it is really much more important, which is derivatives. Okay, so we'll stop it right there, and I'll see you all next time.